In this question, we are given a power plant modeled as a Carnot engine that uses steam turbines to deliver energy, and we are going to find out what effect that has on the river water immediately downstream from the power plant when it exhausts its, shall we say, wastewater, the water that's been heated up through its process into the river. All right, so one of the first things we're going to want to do is convert that power output of 880 megawatts. Let's go ahead and we'll express that in watts, 880 times 10 to the 6 watts. And then the fact that this is going to operate as a Carnot engine clues us into a couple of very important relationships. So the efficiency, I'm just going to go ahead and label it EFF, is equal to, for a Carnot engine, the difference between its operating temperatures, T hot minus T cold, divided by T hot. And for a Carnot engine, this is also going to be related to the heat input at the high temperature minus the heat exhausted at the low temperature, divided by the heat input at the high temperature. But the difference in heat input and output is simply equal to the work done by this Carnot engine. So we have a little bit of a roundabout way, and we are going to end up needing to come back to the temperature differences. Don't worry. But this lets us see that the work that is done is equal to the efficiency multiplied by the heat input at high temperature. So we will be able to find all of this out, right? So, and that comes from the fact that, or I should say we'll be able to find that QH will be equal to the work output divided by the efficiency, right? This is the really key thing. Work is our output. QH is the input energy, and so that's how efficiency becomes the ratio of output to input. So we can now use our temperatures here to find our efficiency. T hot is 625 minus 285 for T cold divided by 625, and I have an efficiency equal to 0.544. So this now will let us find the rate of heat input. So notice that our power out is basically a rate at which work is done, right? It's a work divided by time. So I'm going to take that equation that I just developed for the heat relative to work and efficiency. I'm going to divide both of those energies by time and turn it into rates. So the actual number of joules versus the rate at which the joules are input and output doesn't, it's the same efficiency, it's the same ratio. So my ratio of heat input will therefore be equal to my 880 times 10 to the 6 watts divided by my efficiency of 0.544, and I get a rate of heat input of, I keep some extra decimals while I'm doing my calculation, 1.6176 times 10 to the 9th watts. Well, great. In order to figure out how the water is warmed, we're going to need to know how much water is, or how much heat is exhausted, in case I didn't make that clear before. So our next step then, well, Q cold, what's exhausted, is equal to the difference between the heat input and the work done. That's from this idea right here. And guess what? If we express all of these as rates, well, we can do that. And so the rate at which heat is expelled into the water of the river will be equal to the wattage we just found, 1.6176 times 10 to the ninth, minus our power output of the power plant, 880 times 10 to the 6 watts. And I'm going to get 7.376 times 10 to the 8th watts is the energy expelled into the river. So you might recall from calorimetry that Q equals MC delta T, right? So if we have a rate at which energy is being released into the river, we can then figure out the temperature change. We just simply need to divide my MC delta T side by T for time so that we express it as a rate. And now you might recognize that, well, specific heat's a constant, delta T is the thing we're finding, so we have this mass rate of flow. Clearly, we have to relate our volume rate of flow to mass rate of flow. Well, friends, you might remember that density equals mass divided by volume. So mass will be equal to density times volume. So a mass rate of flow will be equal to density times a volume rate of flow. So for this problem, our mass rate of flow will simply be equal to our density times that rate R that I had before. We are getting there, friends. So we can now rearrange and say that delta T will be that energy rate from a couple lines ago divided by rho times R in place of the mass rate of flow times the specific heat of water. That is a rather large C. Okay, great. And so I can take my 7.376 times 10 to the 8th joules per second. And I'm going to use 997 kilograms per cubic meter as the density of water because 1,000 is for pure water, and river water is not pure water. And then we need the specific heat of water as 4181 joules per kilogram per Kelvin, and I get a temperature rise of 4.78 Kelvin. Okay, I think that covers everything for that part. And now for part B, we are asked to handle the entropy increase. Well, a change in entropy is equal to the heat exchanged divided by the temperature at which the exchange happens, but we're actually asked about entropy per kilogram. So let's go back to this idea that the heat exchange that happened here is equal to MC delta T. So I can take heat divided by mass, and then I have C delta T divided, well, I shouldn't say that. I moved the M to the other side. We don't have to divide on both sides. And so what I can then say is that my entropy increase per mass will then be my heat per mass divided by the temperature at which this exchange happens. And my heat per mass is simply my specific heat of water times the temperature rise of the water divided by that low temperature, the cold temperature at which we're exhausting this heat. So I can take my 4181 joules per kilogram per Kelvin multiplied by my 4.78 Kelvin increase divided by that 285 Kelvin exhaust temperature, and I get 70 joules per Kelvin per kilogram for my entropy increase per mass.